Okay, if you remember last class, we were talking, we started finally talking about the network layer. So last class was mainly talking about the routings in the network layer. So we didn't really we didn't talk about IP layer, IP network, IP protocol, sorry. So today, next week, maybe next week a little bit, is going to be all about IP. And I want you to pay extra attention to this because it's a little bit more confusing than we were talking about the detail of it. So yeah, try to get, and you interrupt me anytime you have questions, okay? Just unmute, tell me the question so you can describe. So what I want to cover today is a little bit of basically why we move toward IPv6. So if you just joined, we are just starting. So I'm going to talk about why we move toward IPv6 and what are the benefits of IPv6, because it's not just about having a larger, basically, pool of IPs. Then I'm going to talk about the classes of the different classes of the IP, a little bit about the net mask, and then we're going to start with a little bit of subnetting, which is literally the most confusing part, maybe, of this course. But let's see how it goes. So the IP version 4 is 32-bit address, 32-bit long. So basically it provides us with 2 to the power of 32, or like almost 4.3 billions of unique IP addresses. So in 2011, we ran out of available IP addresses to assign to new devices, because now you know that even if you look at just the life that you have, looking at 5 years ago and comparing it with now, you see we have tons of more new devices, new services that if they are connecting to the internet, or especially devices, they require IP address. So because of that, how can I say, explosion in the devices that requiring internet connectivity, like you can imagine anything, like, I don't know, your smart wearable devices, whatever it is, smart watch. Then we have phone, not just we have one phone, we have tablet, and we have consoles, different consoles, like a lot of things that require smart TVs, smart, I don't know, refrigerators, that they require IP address for all of them. So basically in 2011-ish, we ran out of IPv4. So we needed to do something. So the question is how? What do we needed to do about it? So the main motivation of moving towards the IP version 6, IPv6, the main motivation was running out of the available IP address for new devices. So the initial idea was, okay, now we have just, we could just assign to 4.3 billion address. We don't have any more available one. So let's make basically a larger pool of addresses, okay, larger address space. So that's the initial idea, or for some of people, they think that's the only thing that IPv6 provides us, but that's not true. So what other things that we did with changing to the IP version 6 was, because we were moving it, we were doing it anyway, we were coming up with a new protocol, IP protocol. Then we said, why we don't fix a bunch of wrong things that we did in IP version 4? Because IP version 4 was not super perfect, okay? You see the protocol stack, how much it was complicated, a lot of fields. So then it said, okay, now we are going to have IPv6, so let's fix some of the problems that IPv version 4 had. So they started basically the work on it, developing it, analyzing it. It started in 1994. The first protocol published in 1998, and from 1999, basically they started adopting slowly to IP version 6. So it has a certain key features. Of course, the first thing is it has larger space, larger address space. It provides us, the address space is 128 bits. So basically it provides us 2 to the power of 128, which is giant numbers. I cannot even say how much is it. So it has a large address space. But that's, as I mentioned, that's not the only thing IP version 6 gave us. So it did other things. For example, it simplifies the header of IPv version 4. So basically what it is, it made less common fields in IP version 4 headers as optionals. It's removed some of them. We don't use it. We don't use in IP version 6 anymore. So we move basically all those unnecessary information that we could move to other basically part of the network. We move it from IP version 6. So it provides end-to-end connectivity because now every system could have a unique IP address. Okay, so because the address space is very large, any device that is connected to the service system could have basically a dedicated IP address. Then it makes like DHCP things like unnecessary. Or if, for example, DHCP server is how to say is down, for example, there wouldn't be any problem with the network. Then it makes auto configuration. So like that one I'm telling about DHCP is about here. So it makes basically absence of server does not, DHCP server does not cause any problem. DHCP is like dynamic host configuration protocol. You can see it in your computer, the one that basically assigning the IP dynamically. About the security, initially it was supposed to apply IPsec to the protocol as a mandatory field. About this IPsec, you're going to see later in your security course. Maybe you're going to work with me on that. We're going to talk about it in the security course. But it's a security protocol for IP layer. But now it's optional field, it's not compulsory. Another thing that I need to mention here, as we simplified the header, so anyone knows how big is the IP version 4 header? The size of the IP packet, let's say?
32 bits?
No, that's the address space. You remember we were having this square with all the fields, source address, time to leave, destination address, the payload and all those things. If you remember, maybe we saw the maximum size can be 65 kilobytes. And the minimum, basically the size of the header itself, just without any data payload of IPv version 4 is 20 bytes, okay? So we know for IPv version 4, version 6, we have 4 times the space for the address, right? But the general size of the IP version 6 is just 40 bytes. It means it's just 2 times bigger than IP version 6. Because we simplified the header, we moved a lot of unnecessary information from the header. So that's being said, this is summarizes like comparing IPv version 4 and 6. It's deployed in 1988. This is basically started deploying in 1999. It is 32 bits IPv version 4 against 128 bits. So address format in IP version 4 is dotted decimal. You already see this. Most probably you have already seen some IPv version 6. But the way that we show IP version 6 is our IPv6. I'm going to say just IPv6 is hexadecimal notations. Basically, each one of these is 4 bits or basically hexadecimal. So then number of addresses is like around 4.3 billion for IP version 4 and trillion, I don't know how to say that, for IP version 6, IPv6. And this is the way that we're going to see prefix notation, and we're going to talk about what this means. I don't know, any of you have seen this type of address? The IP address / number. This is basically a prefix notation for IP version 6 and for IP versions 4 and 6, and we're going to talk what does it mean. So before going there, let's compare IPv4 and IPv6 headers next to each other. You remember we talked about this, the source address, destination address, time to leave, but define how long is packets going to circulate in the network protocol, about what type of protocol is the packet, is the data about, or type of service, what is this packet about, the version, the length, checksum for the security and making sure nothing basically the packet is intact. But if you compare it with IP version 6, you can see it's much, much simpler in the version 6 one. You have destination address, source address. You can see all these reds, basically headers, are removed in IP version 6. So for example, the time to leave change to hop limit. So it's not about time anymore, it's about how many hops basically is going to leave. For example, the packet's going through how many routers before it drops, okay? So you can see it's much simpler, much more easier to understand what's happening in IP version 6 than IP version 4. Any questions so far?
Teacher, why are we not using IPv6 then?
Why we don't use IPv6?
Yeah, like especially with packet tracer, we just use IPv4 addresses.
Because it doesn't matter actually. Okay, you can do that. I mean, I'm pretty sure you cannot do that at some point. I have no doubt, and there should be some activities that you assign IP version 6, but it's just easier to use IPv4 because it's just a concept. Okay, it's not important really. I'm going to talk about it, but I mean, definitely there would be activities with IPv6 because you're supposed to learn formatting, and now basically you're supposed to practice with IP version 6 too. So you're going to see that for sure. So okay, let me show you before I go through this. There is this basically page in Google that you can see how much is IPv6 is applied at the moment, because as you mentioned, it started in like 2009. No, sorry, 1999 to basically standardize. So this graph shows from 2009 that is started like basically using it in the real network, or some services move towards IPv6. So you can see by now it's like around 30% of this. This shows how many of the basically Google users is reaching out to the service using IP version 6. Okay, so we can measure that as sort of like the measure of adoption, how much we adopted to the new version of IPv6. You can see still it's like 30%. It's not everyone in the world is using IP version 6. But you can see we are getting there. As we are going toward the time, we're getting more and more popular with IP version 6. This shows basically which countries are ahead of the time, which are farther, which are using it. For example, in United States, 42% adoption. In Mexico is around 38% of the adoptions. Basically, it means moving towards IP version 6.
There is no information.
Pardon?
In China because Google is banned, no?
You asking questions? I didn't get
it. Google doesn't have information of China because Google is banned, no?
Yeah, most probably. Or maybe I assume that's the reason. Or yeah, that's a weird case. A lot of countries actually, you see, they're not like white people. The one in Asia, the Middle East, not all of them are basically moved. Even you cannot say just it's because of its ban, because there are some other countries too, like maybe either their infrastructure is not that strong, or maybe in the case of China, it can be that can be the reason. I'm not sure honestly why it's too low in China, especially. So let's talk about the IPv6 address representation. So basically, we represented it's 128 bits. So we represented it in the group of 16 basically bits in hexadecimal notations. So basically, each one is like 4 bits, right? In the hexadecimal, each one of these are 4 bits, and in total it's 128 bits. So we divided them basically in the groups of 16. So we get 8 part of. So we get basically 8 parts for our IPv6 notations. So you can see it's quite, like, just considering this one, it's quite large, like a set of numbers compared to IPv6 for how easy it is to How easy is that to say or to remember? But it is a little hard to write it even. So there are two rules to simplify IPv6 addressing. So the first rule is you can basically eliminate the leading zeros in each 16 bits group. So basically, if you look at it, you can eliminate this zero, right? This is the leading zero, so you can eliminate this 30. You can eliminate this 30. You can eliminate this 30, right? So if you make it simplify it, you end up with something like this. Okay, clear?
Okay. Yes.
And there is okay. So we're getting from this long set of basically hexadecimal notations to this, and then there is another rule. It means like which define it like the contiguous group of zeros can be compacted. For example, here these two zeros that are continuous, okay, they are next to each other. They can be compacted, so you can show them like in this way. Okay. So this is what you see a lot more. I mean, almost in all the like IPv6 4, you want to see this because a lot of them are zero. Okay, there are a big chunk of it is zero, so you're not gonna see this type of thing. So when you see this, you know there are zeros that are eliminated here. Okay, and if you know this is like supposed to be 8 parts, so you have 1 part, 2 part, 3 part, 4, 5, 6 parts. So you know there are 2 parts of zeros that are eliminated here. So remember these rules, because you might get this IP address like given you like this, and I say like set it to a, I don't know, in packet traces, set it to a computer, so you know what's happened here. Okay, it's not make you confused what was there. So that's basically finally what we show, or how we represent IPv6. Any questions?
I have a question. So for example, we have like 0001. Would it be omitted, or do we just put the 4 numbers? Then we put it, right?
Yeah, here you eliminate the leading zeros. Okay. So if you see just one number here, one hexadecimal number, you know there are 30 before it that was eliminated. Or if you see like 3 part here, you know there was 10 before it eliminated. But not the after one, right? The after one would skip, because if you eliminate this one as well, then you don't know the 0 was before or it was after. So it doesn't make sense, right? So only the leading zeros, and then this contiguous group of zeros can be compacted. Any other questions?
But in IPv6, there is divided like in IPv4 in a part of network and the part of host, or? Yes,
we're going to talk about it. Yes.
Okay.
Yes, like in IPv4, we said you have network host, network part, host part. In IPv6 also you have network, you have a subnet part, and you have a host part. We're going to talk about it most probably next week, more when we are going so deep into the how to say subnetting. But I'm going to mention a little bit today. So you see we have like the one that I was showing you. Ulysses is totally sleeping. It's falling. So you see that the adaptation was like 33%, the one that I show you in the Google. So basically what it means that IPv4 and IPv6 are coexisting at this time. So there are certain systems that are working with IPv6. There are certain ones that are working with IPv4 still. So there is this interoperability between them. So according to this standard, every IPv4 address has an associated IPv6 address already. So networking stack translates appropriately depending on the other ends. Let me tell you what does it mean. So let me show you here. For example, 2 IPv6 endpoint must have IPv6 stacks. if you have your two endpoint is IPv6 enabled, okay, they are using IPv6. The middle basically systems should be IPv6. If you are going IPv4, IPv4, they are all acceptable. If you're going, basically, if the packet is transferring from the two end host, but through a version 6, it's possible. Okay, there's no problem with it. But the problem would be happen when you have version 6, and in the middle you have some system that's working with only version 4. That's going to be causing some problems. But as we mentioned, there are basically, that's the system, we are using both IPv6, IPv4 at the same time. So there are certain solutions for basically coexisting these two. Okay, this is there are like two methods I put here. This one is IP tunneling, and another is having dual stack. So for example, talking about dual stack, you have both stacks. For example, this is when you are only using the IPv4 stack. Okay, you have IPv4 enabled application, you have TCP UDP in your transmission layer, then you have IPv4, you have Ethernet. That's how it works. But when you have dual stack, you have both IPv4 and IPv6 at the same time. Okay, so they are basically using both. And tunneling is basically somehow encapsulating IPv6 packets into the IPv4 header and transferring that way, transferring your IPv6 packets. Okay, they're not like mostly. I think we're using dual stack. Okay, rarely tunneling. Still, it's used, but much, I guess, lower rate than dual stack. But yeah, there are like certain solutions for making these two protocols coexist together, because moving complete to our IPv6, it takes years and years and years. Okay, because we were using IPv4, now we are going toward IPv6, but it's not just one night like changing, because they have to adopt, different countries should adopt ISPs, all the internet providers should adopt this slowly. So remember these two solutions for basically having these two different way to coexist IPv4 and IPv6. So continuing talking about, let's say, IP or IPv4. Now let's talk a little bit about IPv4. So as we mentioned, the original hierarchy was like network part and host part in the IP. Let's just talk about IP. In the IP, we had a network part and the host part. Okay. So that historically we had like certain class of the IP address. We have like more than 3 class, but as I mentioned, I saw NetAcad is just talking about 3 class. I'm talking about this 3 class because we have class D, and E is way less popular. No one is talking about it. So just remember this 3 class of the IP addresses. So the class A is, we have like 8 bits for the network part and 24 bits for the host part. And the class A start basically with 0 in a network part. Okay, you have a 0 definitely, then you have a 7 bits for the network, then you have 24 bits for the host. In class B, it starts with 10, then you have 14 bits for your network, 16 bits for host, and class C start with 110. You have 21 bits for the network and 8 bits for host. And let me tell you what does it mean. If you have like 7 bits for the host, how many for the network? How many network you can have?
What was the question?
If you have 7 bits for your network part, how many networks you can have?
128, I think.
128, right? Because as you said, you just simplify, like you just simply said 2 to the power of 7, right? 2 to the power of 7, it means 128. But in class 8, we don't have 128. I mean, I'm going to tell you why. Because you cannot put all 0, but all 8 bits 0 is it's a reserved address that you cannot assign to any network. Okay, and That's why we have 124. I'm going to talk about it. So that's anyway, you imagine here you have that number of the network. So then each network can has 2 to the power of 24 hosts, right? So you have 126 network, which has 2 to the power of 100, 2 to the power of 24 hosts. And so in class B, we have bigger type of network and smaller hosts. And in the class C network, class C IP address, we have a lot of basically, I guess it would be around like 4 million something network that has only, how to say, 256 hosts each network. Don't get confused. I'm going to go more detail on this. So you remember the IPs is 32 bits. So we said it's a network part, host part. So in class A, we said it starts with 0. Okay. As I mentioned, all zeros is the reserved address. You cannot define to any network like 00000 address because that is reserved. And this address 0 and 71, or basically translated to 127, is reserved for loopback. Loopback is a certain type of packets that you put your own address that it goes back to the system itself. Okay, but I'm just mentioning here these two are reserved. Okay, so in total we have 2 to the power of 7, which is 128, minus these two reserved address. So we left with 126 network. Okay, and 2 to the power of 24, it means like around 16 million hosts we can have. So what it means here, when I'm talking about the network and host, it means, for example, you have one network. Let's imagine a network of Telcel, okay? So you assign a class A address to Telcel, okay? One class A address to Telcel, then Telcel network now has like 16 million hosts. 16 million. Now this basically IP can assign to this basically IP address that you assign to Telcel, let's say to a company, can has 16 million hosts. Another like 60 million more different connections. So as I mentioned, these are all allocated already. Okay, we ran out of this class A. So class B is start with 10. Okay, so it range basically between 128 to 191, and XXX is, it means like if you put 100, if you start your basically your, how to say, byte here, 8 byte with 10, you get 128. You start from this until this is your range of the address for the network part, network ID part. Then each one get basically this many network you can have 2 to the power of 14 different addresses that you can have. This means like 16,000 network part you can have for network ID, and then the host ID is basically 2 to the power of 16 again, which means all your IP address range going to from 128 to 191, as I mentioned. XXX means like 191 whatever here. Maximum would be 255, 255, 255, right? That would be the range of the IP address for class B. Let's say again, for example, another example I can say, for example, class B. Let's say the one class B IP address dedicated to tech, for example. I'm not saying that okay, but imagine one class B address is dedicated to tech. It means tech can now has assigned like 2 to the power of 16 different hosts that is connecting to the network of tech, as an example. Again, all this class IP address, all this range of IP addresses are allocated already. So we ran out of this. Then class C start with 110 in the network part. So basically, this is the range of IP addresses for class C, starting from 192.0.00 to 223 and 255 to 255, 255. This is the range of the addresses that we can have for a class C address. So here you can have 2 million, like almost 2 million networks, and each network can has like 256 like hosts. Okay, for example, imagine a small company that get a class C address, and this company has, I don't know, 5 floor, and then he can dedicate now 256 different hosts in that network. So it's this is also nearly basically all allocated. That's why we move basically towards IPv6. Any questions so far about this? Okay, this going to be more clear even later, because we're going to talk about this host ID, network ID. Okay, let's talk about net mask and see what does that means when we put an address like this. Okay, so you could, because as we mentioned, when we're talking about an address, in addition to just mentioning address, a device typically also has something, we call it net mask. Basically, a net mask tells the device which IP address are local, okay, in the same network, and which IP address requires for the packet to go through the router to the outside network. For example, considering the network that I have here in my house, I have smart TV, I have smartphone, my tablet, my laptop that are connecting, another phone, okay, another tablet. So okay, so there are all these devices that connecting to the network that I have in my house. So if I'm, for example, theoretically, if I'm communicating between my phone and my laptop, which they are both in the same network, so the packet doesn't need necessarily to go out of my network, my internal network. Does it make sense? Because they are both existing in the same network. So the packet doesn't need to go through all the internet and come back to me. It can just circulate in my own network if I'm communicating between these two devices. My laptop, my smartphone in the same network. So basically the net mask tells us if two networks are in the same, if two IP addresses are in the same network or they are not belong to the same network. So basically a net mask is written as a string of consecutive ones. For example, a net mask of 24, it means 24 ones, consecutive 24 ones. Okay, and that's how we usually represent it. I'm going to talk about it to make it more clear. So imagine this is the net mask of 255,000. Okay, means if the first 8 bits of the network are matching together, two different IP addresses. So what it means basically this one. Let me annotate it here so make it much easier to understand. This one means basically my IP address or whatever it is. Can you see my annotation that I'm putting?
Yeah.
No, teacher. No.
Yeah, the blue.
Some of you see, some of you don't. Okay, let me.
I see it.
Okay, let me not do it.
I see it too. Yeah.
Okay, let me.
Okay, I can see it too.
Okay, let me see what's happening. Annotate, clear all drawing. Second, I can annotate here. Okay, I'm going to use this, whatever. So if this is the net mask, basically it means this is my IP address, okay? If I put it in this format, it means it's the IP address and my net mask is 8, because 255 is like a 8-1, right? So I mean, I'm describing it, then I make it more clear. This net mask means a 16-1, so it will be basically in that format that I put here. it means my IP address, then /16. And this net mask is because 255.255.255.0, it means 24 consecutive ones. Okay, so it will be my IP address. If I put it in this format, then 24. So if you want to, yes.
So for example, in the IP we have at the beginning of this slide, it means that the first 3 octets are the network part, or?
For which one? I didn't get your question.
Yeah, that we have this IP and the /24. So that means that the first 24 bits are the part to see the network.
Exactly, yeah. That means the first 24 bits are the network part. So if you could, if you remember when we were talking about the classing, so basically this is a net mask for class A. This is a net mask for class B somehow. So this is a net mask for class C, right? So the first basically 8-bit in class A address, they were, I think I have it in here. Okay, yeah, let me. No, I should go back. How can I clean this now? The eraser doesn't appear. Let me see. Oh, drawing like that. Clear all drawing. Okay, so if I go next, then the next. So you remember we talked about class A, B, C, and these are the basically value in the first octet. So this was the value in the first octet. This is the net mask for class A, net mask for class B, net mask for class C. So it means this is basically the perfect notation that we use. You put the IP address /8 or IP address /16, IP address /24. So this tells us basically that the first 24 bits are those that are matching the first 24 bits, those IP address that they're matching the first 24 bits, they are existing in the same network. They belong to the same network, okay? So I'm going to talk about this more because it needs to become much more clear. So we don't have just this type of net mask, okay? We can have various type of net mask. Okay, for example, we can have 24. It means all 1, 1, 1, 1, like 24 ones, right? If you put 24 ones, it means 25, 255, 255, 255, right? In a 24 ones in a basically binary, it means 255, 255, 255 in a decimal. 25 means like this, 26 means this, 27. So we can have all these different type of basically net mask, okay, which generate different set of network part, different size of the network part, and different size of the host part. Okay, so just remember this. We're going to get back to this with the questions, which make it more clear when we're talking about this. So I'm asking you this one. So for each source, destination, and net mask, mark whether the destination is the same network as the source. Okay, so we have a source address, IP address here. We have the destination IP address. This is the net mask. Okay, so what I want you to tell me if this source and destination, they are in the same network or they belong to two different type of network. So let's talk about the first one. Let's talk about this.
No.
I think they're in a different network.
Oh, they know.
So who says they are in a different network?
Me.
Okay, so for example, Kevin, can you tell me why you think they are in two different networks?
Well, I think that because we have in our net mask,
Mhm.
255.255. So this means the first two octets are the network pair. So in source we have 128 and the destination 128 is shared, but the 34 and the 35 are different.
Exactly. So how you're looking at it, you say, okay, if I say this 255 here, it means these two parts should be same. This means these two parts should be same, right? Then if they are same, then they are in the same network. If they are not same, they are not in the same network. So basically these two are, they are not in the same network. So what about this one?
They are in the same
Yes,
network.
They're in the same
yes, they
network.
are in the same network.
Yeah, because you're looking at the first three decimal part, right? Say this one, this one, this one, and this one, this one, this one, they are equal. So they are in the same network. So this one,
Oh,
No.
they are not in the same network, right? Because these two and one, they are not same. Okay. So what about this one?
I think they're in a different network.
So why do you think that?
Well, I'm not sure because this net mask ends with 2 to 4, but I mean that until that number it have to be the same, like the source ends with 33 and the destination with 5. So I think it's different for that. I don't really
Okay.
know because I don't know what the hosting is here.
So anyone has answer for this? Any of you guys? Okay. So this, yeah, this case becomes a little bit more complicated because okay. Let me, okay. So this one gets more complicated because you're looking at, if I turn on, you're looking at this, you said 255, 255, 255, you're using the same mindset, the same basically concept. You say, okay, these first three parts should be same. Then you're looking at it and you say, okay, the first three parts are same. So what the heck is this last one, right? So you remember the net mask is, when we're talking about net mask, this net mask means 224 here. What is 224 in terms of binary? One. What would be the binary of 224? It would be one, there's like 128, another one in like 64, another one like 32. You sum them up, you become 100, 224, like this, right? This is the 224, right?
okay.
So we have a basically, this is in the binary. This is the binary of 224. This is equal to 224. Can you see the notation?
Yes.
Yes.
Okay, so that means 224. Okay, so it means, so what is the net mask for here? If I want to put it in the format of like this, like dash something. It's like my IP address dash something. If I want to put it in this format, what would be that something here?
27.
That's 27, right? You say, okay, the first, this is like 8-1 here, 8-1 here, 8-1 is like 24-1. Then I have another 3-1, so this would be basically 27. So it's the net mask is 27 here. I mean, that number would be 27. So then how you calculate if these two are in the same network or not? Okay, you have this.
Teacher,
Yes.
why 27?
Okay, let me. Pen. I'm trying to find this so I can just write it in this. Okay, why 27? Because this 255 here, okay. This 255, oh God. This 25, I think I should close this. This 255, okay. This means like 8-1 in a binary format, right? This 255 means another 8-1 in a binary format. This is another 8-1 in a binary format. So we have
16.
this address is basically, if you convert this address in a binary, you get 27-1 and then like a 5-0. That's in the binary format. So that's why
Okay.
that 24 comes from there, okay? So but anyway, you want to calculate these two networks are in the same network or not, you can use this method. You can basically, okay, let me again use the annotate text. So you want to calculate if these two are in the same network or not. Basically, you can get this address, okay, and do and logical AND between these two parts of the network. Because the first three parts is so clear, right? You know, this three part, the first three parts are the same. The only question is the last part, okay? So you can get, okay, this is your 224, okay, the net mask. You get the source. This is the source. So 33 in a binary would be basically 132 is like 2 to the power of, what would be 33? 0, 0, 0, 1, 0, 0, 0, 1. Or, no, sorry, this one would be this. So this is 33, right?
Yes.
This is 33 in the binary. If you get these two, okay, this is the 224, this is 33. And if you get this and do the AND operation, okay, between these two, you get 0, 0, 1, 0, 0, 0, 0. 0, right?
Yeah.
Is it clear what we did here? We did AND operation, logical AND between these two, okay? So you get this. But if I do the logical AND between 1, 1, 1, 0, 0, 0, 0, 0, okay, and if I get this and I do logical AND between this, it means 0, 0, 0, 0, 0, 1, 0, 0. What would be the 5 in binary? I'm losing my mind. Like 4 and 1, right? So this is 5, right?
Yeah.
Right? So if you do basically AND operation between these two, you're going to end up with 0, 0, 0, 0, 0, 0, 0, 0, right?
Yes.
That's an AND operation between these two. And then if you compare these two, basically, if you compare this one with this one, you see they are not same. Basically, that's it's too long to come to this conclusion, but that means they are not in the same network. Okay. Adalberto is like is so exhausted of long descriptions, right?
Teacher, so
Yes.
I have a question.
Yes.
So if you have an IP address and then /30, that means that you can only have 2 hosts.
That means you can only have 2 hosts, right?
So you can also take that last octet and turn and have even more networks.
Yes,
Like
yes.
there are more types than type C.
Yes, I'm going to talk
Beyond
about
type
it.
C.
It's not, when we're talking about it, it's not just, I mean, it's not just class A, class B, class C, okay? That was basically all the structure of the network. Those earlier days when we were basically using IP addresses, there were not a lot of systems that were connected to the internet. There was a lot of IP address available, 4 billion. Who was thinking that we're gonna run out of it one day? No one could think that's going to happen in the future. No one could even predict that, okay? So they were assigning like this type of IP addresses. For example, those early institutions that they started using IP addresses, like, if I'm not mistaken, Berkeley, Harvard, they get class A address, okay? So it means they get an IP address, now they can assign IP address to 4 million users. Of course, they don't use it, right? Of course, they don't have 4 million users. So those days it was no problem because we had a bunch of IP address available, but now this problem, okay? So we move away from that basically class A, class B, class C, so we can have different type of IP addresses, different type of net mask, as I put here, for example. This doesn't fall to any of the classes. This would be like different, right? So anyway, long story short, talking about, let me clear all, close this, do pen. So we said this was in the same network or not? This was no. This was yes.
Yeah.
This was
Not.
This
No.
was the last one.
No.
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 No. I mean, don't get too confused. It took me long to explain it, but if you're just looking at it, and if you're too fast converting decimal to binary, you can know this is like this comes, for example, the first one would be from the left hand side would be in a third location. Okay, 224 is like 111,000. Then you know if you add this and this, you're gonna get 1 in the basically 6th location, then all 0. 5 is of course just the first 4 bits in the right hand side, then you're gonna get 0. It's going to be very obvious. What about the last one?
It's yes. Yes.
And when it comes like this, it's much easier to say, okay? So now, what I hope you to take away from so far, okay, is how it works. The net mask, what does it mean? It means if there are 2 IP addresses belong to the same network or not. It helps us with tons of things. You remember we were talking about routing information. You wanna get, for example, you wanna plot or multicast the packet. So the packet doesn't need to go out of certain network to go and circulate all over the network, internet, okay? The packet can stay in the network that is designed for it, okay? It belongs to, okay? So those things, for example, if I have source address like this, net mask like source address like this, net mask like this, then I know these 2 packets belong to the same network. If I'm doing the broadcast, okay, it means this broadcast packet should stay in this network. That's simple as that. So it helps us with tons of things. And yeah, we're going to see more, okay? So I'm just going to talk about this, then having a short break, then continuing a little bit more. So this is, okay, what the address structures today, okay, that things that I said, class A, class B, class A, B, C, still we have it, but it's not just those options because they were too coarse-grained. As I mentioned, for example, imagine a university, you get a class A address. Of course, you don't want to use it, so basically, it's not efficiently used the number of the address. So then they come up with this classless interdomain routing, or CIDR. Okay, that could have different type of net mask, okay? Let's say. Not just like 8, 16, 24, it could have the variable length of the basically host number, network number and host number. So do you want a short break or should I continue and finish earlier on the other side? Oh, no
I
opinion?
prefer you to continue.
Okay.
Continue. Yep.
Okay, so let's continue. At the end, we're going to end up earlier. So anyway, you might wonder, we are dedicating IP address to different system, computer, mobile phone, smartwatches, and different network, different countries, and who is basically organizing all this all this management. Okay, basically we have this type of organizations. For example, IANA, Internet Assigned Numbers Authority. We have this type of basically regional internet districts. Okay, that they define for different continents. For example, for Africa, we use this. For ARIN is for USA, Canada, North America. Then APNIC, LACNIC for Latin America. So they are basically different organizations that they are handling the IP assignments. Okay, because at some point it should be managed by a certain organization. Okay, for example, if I'm one company, if every one of us has one company with thousands of hosts that we need IP address to assign to them, and we start just assigning randomly whatever we want, it doesn't going to work because at some point it's going to be duplicated or it's going to be problem by that. Okay, so there are these basically authorities that they're handling all this assignment. So should I talk about this now? All right, let me talk about a little bit of subnetting. Okay, but we're going to talk about it later, way much detail and way more confusing later on. So if you consider this, I mean, we already saw this part. Okay, we had a basically network portion. Okay, and we had a subnet portion. Oh, sorry, this is confused. That line should be here. So we have the subnet portion. We can have a host portion of the IP address. So let's say like in the beginning of the network, like the board, the network was flat. Okay, so you get basically, different type of IP classes like IP class A, B, C, or depend on your need, you get one of those on those early days. And as I mentioned, when we had plenty of IP address, there was no problem by assigning IP address like this. So then, but in basically in 1985, IETF provides process for subnetting, basically breaking up the network into smaller networks. So subnetting was not something that they thought about it from the early on. It was an afterthought for IP version 4. That's not the case for IP version 6. We're going to just talk about it. Subnetting basically means you want basically somehow break down the network into a smaller network. Okay. So it's the subnetting is basically segmenting a network in subnets or subnetworks, creating a smaller group of devices in order to control traffic better, okay, into our smaller network, reduce overall network traffic, and improve performance overall. So these are basically, subnetting helps us with creating a smaller broadcast domain. Let me make it clear. When we're talking about subnetting, you can imagine it like this. And tech, if you haven't forgotten yet, there's still tech. Okay, how was it? Hidden network is just imagine tech as a whole organization in Mexico. It's an organization. Hidden is a network. You want to create a network. Now this network, the main network, can be break down into different campuses. Okay. So we have now campus Monterrey, Querétaro, Guadalajara, Ciudad de Mexico. So we have all these campuses. So each one can get another basically subnet. Each one can be one subnet or subnetwork in this big network. And then campus Guadalajara, let's say, wants to dedicate one subnet, a smaller network, even inside itself, to, I don't know, for example, to Aulas 1, a smaller network to Aulas 2, a smaller network to Aulas 3, and all this breaking down the network, okay, because we mentioned earlier it was flat, but now we want to break it down. Why we want to do that? Because it makes us to achieve all these goals. It makes us to manage the network much better, because now we have this hierarchical structure of the network. Okay, so you can manage it better. It creates a smaller broadcast domain. Let's say there is a packet, only should broadcast it through all the hosts that are in campus Guadalajara. So they don't need to go to all the campus across Mexico. Okay, the packet can be only broadcasted in campus Guadalajara. For example, they are doing certain, I don't know, they are testing a network. Okay, there is a problem in the network, they want to test, they want to send a packet to all the network, let's say ping packet, all the network that are in the Tech Guadalajara to make sure what's happening there. So the packet can just circulate inside. So we have basically a smaller broadcast domain if we use the broadcast packet. We limit the amount of traffic on the other network segment. By using that, then the network in the Monterrey campus is not going to be busy with what we are doing here in Guadalajara. It provides low-level security, even the security-wise, it helps us to manage it better. So it helps us a lot. Even it makes it easier for the future growth. For example, okay, I'm going to maybe, I don't know, you know or not, in the future, there are going to be new buildings in tech. Those massive parking slots that we have, there are going to be few buildings growing in that part, that the parking slot in campus Guadalajara. So those are going to be new buildings. So let's say it would be much easier to manage it. Okay, for example, for any building that you're creating there, you define just a subnetwork. That easy, right? Then that subnetwork will be part of your main network. It makes it easier to manage, it makes it easier to do a lot of things. So just as a note, remember when we use this term subnet and network, it can be basically interchangeable, okay? Subnet and network. So if I refer to them either as subnet or network, you understand what I'm talking about. Okay, so let's move on. So basically, if you have this network, let's say this is your network IP address for your ISP. Okay, so imagine this is the network address in the tech that we have. So the internet provider for the tech just sees this addressing for the tech as a whole. Okay, but what's happening inside this network here? Okay, it's sort of hidden from the internet provider. That small network can be basically break down to all this subnetwork that we have, but still it doesn't change anything for the internet providers. Okay, internet provider is going to see this address for all these networks. These are the basically network address. They are the host address here. You remember? Is that 16 is means these two, the first two parts are the network address. Now you can have, for example, 2 to the power of 16 host address inside. But what can happen inside this network is, this network is again the breakdown into a smaller networks. Now inside this network, we have another 5 different networks. So for these smaller subnets, okay, we have this as a basically subnet mask, which means now this one, also this particular set of bits in the third location are also part of the network. So you see what we are doing? We are doing basically subnetting Then we're going to again be doing another subnetting. Even this particular network itself, it could be breakdown into different, basically different networks. For example, this could have another 3 subnets. Okay, for example, it could be IP like I don't know / for example 27. Okay, so another network. So basically, what we are doing, we're breaking down, making a smaller. It's like a hierarchy. It's like a tree. We have big one. We can be breaking up into smaller branches.
So, for example, for instance, in this example, we can have 255 subnetworks. So adding this. Okay.
You mean in these subnetworks here?
So yeah, so we have our original IP from the ISP. We are saying that we use the third octet to make subnetworks.
Yes.
So we can have up to 255 subnetworks.
Exactly, for this one. If we're doing this one, then I said, for example, for this one, again, I can go and break it down, right? You remember it was not just 8, 16, 24. I can go 27, right? Like the one that we saw earlier. You remember this example?
And in theory, we can connect the same total number of devices, only in different subnetworks.
In theory, yeah, the number of devices won't change, right? But the management would be much easier. Because you have, for example, as I mentioned, you have one network for Tech Guadalajara, then another smaller network in that one for Aulas Uno, another one for Aulas Dos, Aulas Tres. Each one has one basically dedicated network, how to say, subnet, make it much easier to manage and organize it. So you can see it, okay, you can see basically as that's exactly your question. If we have 100 apples, a barrel of 100 apples, I can break it down to 10 baskets of 10 apples per basket. I can divide it into 5 baskets of 20 apples per basket. I can divide it in 5 baskets of 20s, okay. Then this last basket here, I can break it down to smaller, to 2 baskets of 10. Is it, you got it? At the end, the size doesn't change. I'm not generating new IP addresses. I'm just organizing it better.
Okay.
Is it clear?
Yep.
Okay. So that's make it much easier to basically organize, but nothing new is generated. Still, the number of the IP that I can use stays same. Let's say that. Okay. So for doing that, okay, you need, for example, let's say you're become a, how to say, responsible for designing a network for a new company, okay, and they ask you, okay, this is our IP address, this is the network address that we have, this is the range of the address that we have, we can use. So how you can manage it? So in order, for example, okay, you say, okay, I want to generate 8 networks of 20 hosts, okay. But that depends on basically a lot of factors. For example, you need to know, for example, organizations of, in order to do that, basically you need to know the requirement of the network, okay. You need to consider, for example, the number of the hosts per subnet. For example, they say, okay, you design the network for Tech Guadalajara, then you say, okay, I want to define each one subnet for each building. Right? But then you don't say, okay, I design this, I define one subnet for Aulas Uno, okay. Then I just assign them, like, they can just have maximum 16 hosts. Then you say, no, it's not possible, because in Aulas Uno, for example, we have 32 different classes. Each one has a projector that is connected to the internet, that people are connecting their, like, laptop, so it's not possible. So you need to know those things, those information. What is the number of the hosts? How is the basic organization of the network? Maybe that's the information you want to use it in order to break down better the network. So this is basically some idea how one can define or decide what type of host or network or subnetting is going to use for certain network. So not important. Let me just skip some of them. These are the things I mentioned already. These are the things we mentioned. Because I'm skipping because I'm going to dedicate the whole things just about subnetting, because what we see here is basically what we did is like scratching the surface a little bit. When we go down, it's going to be a little bit complicated because we can have different type of subnet, different size of it. We can have a dynamic one. It's like a little bit confusing, but that's why I'm going to talk much more later. So that's why I'm skipping this slide, because at the end I want to keep it shorter. Okay. Let's say that's all from subnetting. Okay, we talk about IPv4, IPv6. Okay, then we talk about different classes, network mask, and a little bit of subnetting. Okay. Any questions about those topics?
No.
So what I want, at least for today, what I want you to understand, to take out from here this class is, you already know if they are belonging to the same network or not. You already know what this means as a net mask. You already know that /16, what does that mean? If I give you, this is the, for example, this is the IP address, then this is like 16, okay? This is exactly same meaning with this, okay? If I write it like this, it's exactly same thing. Same thing that I give you net mask. You got it? So if I give you this, if I give you this and I say, okay, if this one is in the same network with this, then you should be able to say, because you have it here. It's the same thing if I say this is the net mask. Okay, so that's it, that you already got this. So any questions about this?
Teacher, I just have one question.
Yes.
in the quiz.
Mm-hmm.
In the one we saw, the 224.
Okay.
When you put 224 and then the 33, and you, I don't know if you, I don't know what did you do there?
I mean, I said that for the idea, if you want to decide if these two networks are, if these two IP addresses belong to the same network, you can use basically AND operation, logical AND. You can basically logically AND your IP address with this one and this one with this one, and see if the result is the same. So it means they are in the same network.
And how AND works?
For example, okay, AND operation is like if I AND 0. Anyone knows logical AND? It doesn't know logical AND? Jesus Riquelmer?
What do you mean by logical AND?
And when you, it's a logical operation, okay? The add,
binary AND in this case.
Binary operation, yeah.
Well, a binary AND, it's an operator that when it receives two high or on or one, I don't know, or true values.
So 0 and 0, what would be the result if I do this?
0.
So 0 and, oh, sorry, 0 and 1.
0.
Yeah, so it's so you guys know 1 0 0.
Also 0.
1.
1.
So basically, that's when I'm talking about like a logical AND or adding up them logically or binary operation. That's what it means, right? And you know,
Okay,
OR
okay.
is working different way, XOR working different way. So if you basically, if you consider this, and if you, for example, when we said these two networks are in the same place, even when we said these two are in the same network, so it exactly turns out the same result. If you AND this with this and AND this with this, you're going to get the exactly same results, because you know 255, 255, 2555. It's all one. Like it's like 24 1, and you add anything with the 1, you get that one. Basically, if you AND anything with the 1, you get the same result. If you 0 and 0 and you AND it with 1, you get 0. If you do 1, you AND it with 1, you get 1. So what you want to get here, if you AND this one and this one, you're going to get 10.0, 0.1, 0.0, because this is all 1. So that's the same thing that we use for this one. For 224 is like 1, 1, 1. Basically, this one, it means just the just the last octet is like 1, 1, 1, 0. This is 224 in a binary.
Yeah.
So if, and we said that 333 is what was that? 0, 0, 1, 0, 0. This is 333. Yeah, right? Or no?
With 0 extra.
Yeah. So if you basically add them up logically, you're gonna get, this would be, the result would be 0, 0, 1, 0, 0.
Okay, okay. I got it, teacher.
Okay, but if you do the 5 with this, you're going to get all 0. Then you say, okay, that is all 0, this is not all 0, then so they are not belonging to the same network. It's rarely, to me, if you get the concept and if you are really good in converting binary, like just mentally into the decimal into the binary, you can just by looking at it, you can guess if they are belong to the same or not. And there are some tricks, maybe I talk about it later, just doing it, not going through this painful process. Any more questions?
No.
Okay, perfect. So that's it from today. That's why I was trying my best to keep it shorter, making it shorter.